The universe is a mysterious place, filled with phenomena that continue to baffle scientists and spark the imagination of stargazers. From distant galaxies and eerie signals to strange objects within our own solar system, space holds countless puzzles that challenge our understanding of how the cosmos works. Some of these enigmas defy the laws of physics as we know them, while others hint at forces and processes we've yet to fully grasp. How did a supermassive black hole form so quickly in the early universe? Why does a dwarf planet spin so fast that it's squashed like a football? What are the strange, ghostly X-rays that seem to echo across space? And could Venus, with its scorching surface, actually harbor life in its clouds? These questions and the mysteries they point to are more than just puzzles. They may hold the key to understanding the universe itself. Join me as we journey through these unexplained phenomena. Dark matterless galaxies. In the vast reaches of the universe, most galaxies are expected to follow a simple rule. Dark matter holds them together. This mysterious substance, which cannot be seen or directly detected, is thought to account for roughly 85% of the universe's mass. Despite its invisibility, scientists believe dark matter provides the necessary gravitational pull to prevent galaxies from flying apart. But what happens when a galaxy appears to lack this essential component? Recent discoveries have baffled astronomers and cosmologists. Galaxies have been found that seem to contain little, if any, dark matter at all. This is profoundly puzzling, especially when you consider that dark matter is thought to be the very glue that holds galaxies together. According to current scientific models, without enough dark matter, galaxies would be unstable. Their stars and gas would drift apart, as the visible matter alone doesn't seem to generate enough gravitational pull to keep them intact. These dark matterless galaxies defy what we've long believed about the formation and stability of galaxies. How can these structures continue to exist without the invisible mass that seems so essential elsewhere in the universe? The discovery of these galaxies has opened up a series of questions and challenges, pushing the boundaries of our understanding of the cosmos. Astronomers first identified one such galaxy in 2018, known as NGC 1052 DF2. This galaxy, about 65 million light-years away, was expected to follow the same rules as others. Scientists measured the movement of its stars to calculate how much mass should be present to account for that motion. The shocking result? The galaxy seemed to be nearly free of dark matter, a finding that sparked excitement and skepticism alike. It contradicted the fundamental theory that dark matter is essential for galaxy formation. What makes these galaxies mysterious is not just their lack of dark matter, but the fact that they haven't torn themselves apart. According to the current models of gravity and mass distribution, galaxies without dark matter should have long since scattered into the void of space, unable to stay bound together. But these galaxies remain intact, and scientists are left grappling with how such structures can exist. Is it possible we've misunderstood the very nature of dark matter? Or is there something else going on entirely? The implications of these galaxies without dark matter could be far-reaching. Dark matter is a cornerstone of modern cosmology, an explanation for the unseen mass that affects galaxies' gravitational behavior. Without it, our models of the universe would need serious revisions. What if these galaxies are signaling a flaw in our understanding of gravity itself? Could it be that the laws we take for granted, which apply so well on Earth and within our solar system, might not hold up when looking at the universe on a grander scale? This discovery also forces us to ask whether dark matter itself might be more elusive than we thought. Are there conditions under which galaxies can form and exist without it? Or are there other forces at play in these galaxies that we've yet to comprehend? The answers remain unknown, and the mystery deepens with each new observation. One possible explanation is that these galaxies somehow formed in regions where dark matter is sparse. But if this were the case, how could that happen? We've always thought that dark matter was the dominant force in shaping galaxies. For one or two galaxies to defy this expectation is one thing, but as more of these dark matterless galaxies are discovered, the mystery only grows. Another idea suggests that these galaxies might still contain dark matter, but in a way that evades our current methods of detection. Could it be that the dark matter in these galaxies behaves differently, clustering in ways that don't align with what we expect? If so, this would point to a need for a deeper understanding of dark matter's true nature, which remains one of the most elusive questions in physics today. Then, there's the unsettling thought. What if dark matter isn't what we think it is at all? If galaxies can exist without it, could this force us to reconsider the entire concept of dark matter? What if the unseen mass isn't made up of some unknown particle, but is instead a manifestation of something entirely different, like a new kind of force or interaction that we haven't yet discovered? Such questions bring us to the heart of scientific inquiry. While these dark matterless galaxies challenge what we know, they also remind us of how little we still understand about the universe. Every discovery in astronomy seems to raise as many questions as it answers, and this is no different. Dark matter is, at its core, a concept built on indirect evidence, the way galaxies move, the way light bends around unseen objects. But what if this evidence is leading us down the wrong path? Perhaps we're missing something fundamental about how gravity works on cosmic scales. Maybe the galaxies we see are hinting at a deeper truth about the universe, one that we've yet to uncover. Could it be that our entire understanding of gravity, which has stood firm since Newton and Einstein, is incomplete? These are not easy questions to answer, and each hypothesis seems to open the door to even more profound mysteries. Tabby's star, alien megastructure, or cosmic oddity? In the constellation Cygnus, about 1,470 light-years away from Earth, lies a star that has captured the attention of scientists and stargazers alike. Known as Tabby's star, officially named KIC 846-2852, this star behaves in a way that defies explanation. The strange dimming patterns of Tabby's star have sparked intrigue and debate, leading some to wonder if its behavior might be caused by something far beyond the ordinary, perhaps even the work of an advanced alien civilization. The story of Tabby's star begins with the Kepler Space Telescope, which was launched by NASA in 2009 to search for Earth-like planets. The telescope continuously monitored the brightness of over 150,000 stars, looking for the telltale dimming that occurs when a planet passes in front of its host star, blocking a small portion of the light. While Kepler found thousands of exoplanets this way, Tabby's star stood out for a completely different reason. Unlike the predictable dips in brightness caused by planets, Tabby's star exhibited strange and irregular dimming. In some cases, the star's brightness dropped by as much as 22%. This is far greater than the dip caused by a planet, which typically results in a decrease of only about 1% of a star's light. Moreover, these dips didn't follow a regular pattern, making it unlikely that a planet or a simple natural object was responsible. What could cause such dramatic changes in the star's brightness? One theory that gained attention, at least initially, was the possibility of an alien megastructure. Some scientists and researchers speculated that the irregular dimming might be the result of a massive structure built by an advanced civilization, possibly something akin to a Dyson sphere. A Dyson sphere, first proposed by physicist Freeman Dyson in the 1960s, is a hypothetical structure that could be built around a star to capture its energy. If such a structure were in place around Tabby's star, it might explain the unusual dimming, as parts of the structure could block the star's light in irregular intervals. The idea of an alien megastructure quickly captured the public's imagination. After all, the thought of detecting signs of intelligent life beyond Earth is a thrilling prospect. But as exciting as this theory was, most scientists were cautious, pointing out that there are likely far more natural explanations for the star's behavior. The alien megastructure hypothesis, while popular in the media, was largely dismissed by the scientific community as too speculative. Still, The mystery of Tabby's star remains. If it's not an alien megastructure, then what could be causing the star's strange dimming patterns? One of the leading theories is that the dimming might be due to a large cloud of dust or debris passing between the star and Earth. This could account for some of the irregularity in the star's brightness. But there are problems with this idea too. For one, dust typically absorbs and scatters light in a specific way, affecting different wavelengths of light differently. Observations of Tabby's star, however, show that the dimming affects all wavelengths of light almost equally, which doesn't quite fit with the dust theory. It is also possible that Tabby's star might be surrounded by a swarm of comets or other icy bodies. These objects could form a cloud that periodically blocks some of the star's light. But again, this explanation has its challenges. For one, the sheer number of comets or debris required to cause such significant dimming seems improbable. And even if such a swarm existed, it's unclear why it would behave in such a strange, irregular way. The mystery deepened when further observations revealed that Tabby's star wasn't just dimming in short bursts. Over time, it has been gradually fading by about 20% over the course of a century. This long-term dimming, combined with the star's irregular short-term dips, only adds to the puzzle. If not dust, comets, or alien megastructures, what could be responsible for the strange behavior of Tabby's star? One idea is that the star might be undergoing some sort of internal process that we don't yet fully understand. Stars, after all, are complex and dynamic objects, and there's still much we don't know about their behavior. Perhaps Tabby's star is in a unique phase of its life cycle, or maybe it's experiencing something entirely new, a cosmic phenomenon that has never been observed before. These questions lead to a fundamental point. The universe is vast, and our understanding of it is still in its early stages. With every new discovery, we uncover more questions than answers. Tabby's star is a perfect example of this. It has forced scientists to re-examine their assumptions and consider possibilities they might not have previously entertained. While the alien megastructure hypothesis is no longer considered a serious contender, the curiosity it sparked serves as a reminder of the importance of keeping an open mind when it comes to the mysteries of the cosmos. Even though the alien explanation has been largely set aside, the odd behavior of Tabby's star continues to baffle astronomers. It's a reminder that, as much as we've learned, there's still so much more to discover about the universe and its workings. Could Tabby's star be pointing us toward a new type of cosmic event? Perhaps something we've never seen before? Or are we simply missing something fundamental in our understanding of how stars behave? The truth is, we don't yet know. Tabby's star remains one of the most perplexing objects in the sky, defying explanation and challenging our understanding of stellar physics. Quantum fluctuations in the vacuum of space. In the vast, silent stretches of space, far from the heat of stars and the pull of planets, it's easy to imagine nothingness, a complete empty void. But even in the most remote corners of the universe, where it seems nothing could possibly exist, the reality is far more complex. Quantum physics tells us that even the emptiest regions of space aren't truly empty. Instead, they are teeming with activity on a microscopic scale. This strange, unpredictable behavior is known as quantum fluctuations, and it reveals a mystery that challenges our traditional ideas of emptiness. At the heart of quantum fluctuations is the idea that space, even in a vacuum, is never truly void of matter or energy. Instead, particles are constantly appearing and disappearing, flickering into and out of existence in a process that happens so quickly we can't directly observe it. These particles, known as virtual particles, are a key feature of quantum theory. They exist for only the briefest of moments before vanishing again, and their presence suggests that the fabric of space itself is alive with hidden energies. What makes quantum fluctuations so puzzling is that they seem to arise out of nothing. In classical physics, we think of a vacuum as a space completely devoid of matter, but quantum mechanics, the branch of physics that deals with the smallest particles in the universe, tells us that this is an oversimplified view. Even in the vacuum of space, random energy fluctuations cause pairs of particles and antiparticles to spontaneously pop into existence before quickly annihilating each other. This process, while fleeting, plays a crucial role in shaping our understanding of the universe at the smallest scales. The concept of quantum fluctuations is hard to grasp because it defies our everyday experiences. We are used to thinking of things in terms of cause and effect. But at the quantum level, particles can exist without any apparent cause, appearing and disappearing in a chaotic and unpredictable manner. This randomness is a fundamental aspect of quantum mechanics, a branch of physics that describes the behavior of particles smaller than atoms. It's a realm where the rules of classical physics, rules that govern planets, stars, and everything on a larger scale, simply don't apply. Quantum fluctuations also hint at something even more profound: the possibility that these tiny, brief appearances of particles could hold the key to understanding the origins of the universe itself. According to some theories, entire universes could, in theory, spring into existence from these fluctuations. The idea is tied to the concept of the multiverse, a theoretical framework in which our universe is just one of many, each potentially born out of quantum fluctuations in an otherwise empty vacuum. While this remains speculative, it's a tantalizing possibility that has captured the imagination of many cosmologists. One of the most striking aspects of quantum fluctuations is the energy they seem to contain. This is known as vacuum energy, a mysterious form of energy that exists even in the apparent emptiness of space. Although this energy is difficult to detect directly, its effects can be observed in phenomena such as the Casimir effect, where two metal plates placed very close together in a vacuum are attracted to each other due to the pressure exerted by quantum fluctuations between them. This is just one example of how the seemingly chaotic activity of particles in empty space can have real, measurable consequences. The concept of vacuum energy is closely linked to one of the greatest mysteries in cosmology: dark energy. Dark energy is a force that appears to be driving the expansion of the universe at an accelerating rate. Some scientists believe that quantum fluctuations and vacuum energy could help explain the nature of dark energy, though this remains an area of ongoing research and debate. If vacuum energy is indeed related to dark energy, it could hold the key to understanding why the universe is expanding faster and faster over time. But the mystery of quantum fluctuations goes even deeper. Some scientists suggest that these fluctuations could be linked to the very structure of space-time itself. According to quantum theory, space-time, the fabric that makes up the universe, is not smooth and continuous, but rather grainy and fluctuating at incredibly small scales. This idea, often referred to as quantum foam, suggests that space-time itself may be subject to the same unpredictable behavior as the particles that flicker in and out of existence. If true, this could fundamentally change our understanding of how space and time work on the most basic level. But if the universe is fundamentally random at the quantum level, what does this mean for our understanding of reality? Does it suggest that randomness and unpredictability are at the core of the universe's very existence? Or are we simply missing a deeper level of order that we have yet to discover? It would be interesting to hear your theories on this. The idea that the vacuum of space is filled with hidden energies and random fluctuations challenges our concept of nothingness. What we once thought of as empty space is actually a sea of activity, with particles constantly appearing and disappearing in ways that we're only beginning to understand. These fluctuations might seem insignificant, but they could be the key to some of the biggest questions in science, from the origin of the universe to the nature of time and space itself. The more we learn about quantum fluctuations, the more we realize just how little we know about the nature of the universe. While these fleeting, momentary bursts of energy might seem small and unimportant, they could hold the answers to some of the greatest mysteries in physics. The cosmic cold spot, a fingerprint of another universe. Within the universe, there is a region that has left scientists scratching their heads for years. Known as the cosmic cold spot, this area spans a staggering 1.8 billion light-years across and is significantly colder than the space around it. Discovered in 2004 through observations of the cosmic microwave background, CMB, the faint radiation left over from the Big Bang, the cold spot presents an unusual dip in temperature that defies easy explanation. The cosmic microwave background is one of the most crucial pieces of evidence we have for the origins of the universe. It's a relic from when the universe was just 380000 years old, a snapshot of the early cosmos that shows us what conditions were like shortly after the Big Bang. The CMB is remarkably uniform in temperature, only varying by tiny amounts, typically just fractions of a degree. However, the cosmic cold spot is a glaring exception to this rule. It's colder by a significant margin, a full 0.00015 degrees Celsius colder than its surroundings. While this might not seem like much, on the grand scale of the universe, it's a huge deviation that demands an explanation. What could cause such a dramatic drop in temperature over such a vast region? This is where things get complicated. Theories abound, but none have fully explained the scale of the anomaly. One of the most fascinating and speculative ideas is that the cosmic cold spot could be a sign of something far more profound, a collision between our universe and another. Some cosmologists have suggested that if the multiverse, a theoretical collection of multiple universes, exists, then interactions between these universes might leave detectable marks. The cold spot could be one such mark, a bruise left over from when our universe brushed up against another in the distant past. If true, this would be one of the most groundbreaking discoveries in modern science, providing concrete evidence that our universe isn't alone, but just one part of a much larger, infinitely more complex multiverse. The multiverse theory is deeply speculative and, as of now, lacks direct proof. Yet, the idea of universes colliding isn't as far-fetched as it might initially seem. In fact, in some models of the multiverse, it's entirely possible that universes might occasionally interact with one another, leading to observable anomalies like the cold spot. In this scenario, the strange drop in temperature could be the cosmic fingerprint of another universe passing through our own, leaving behind an imprint in the cosmic microwave background. This possibility raises some of the biggest philosophical and scientific questions imaginable. Are we part of a vast collection of universes? Could there be other universes with different laws of physics, different forms of life, or even different versions of reality itself? But not everyone is convinced that the cosmic cold spot is evidence of the multiverse. Another, more grounded explanation is that the cold spot is simply a large void, a region of space with far fewer galaxies, stars, and matter than average. Voids are common in the universe, forming as matter clumps together in some areas, leaving other regions relatively empty. These voids can stretch across millions of light-years and have a subtle effect on the CMB by slightly cooling the radiation that passes through them. However, the cosmic cold spot is puzzling even in this context, because if it were merely a void, it would have to be much larger and emptier than any void we've ever observed. Even the largest voids we know of can't account for the full scale of the temperature drop in the cold spot. The void theory remains one of the more popular explanations, but it still leaves many questions unanswered. Could there be something unique about this region of space, something we don't yet fully understand? Is it possible that the cold spot represents a different kind of void, one shaped by forces or conditions we haven't encountered before? These questions highlight the limits of our current knowledge and the need for further exploration. Another possibility is that the cold spot could be a statistical fluke, a rare but natural occurrence that just happens to stand out in the data. The universe is vast, and the CMB covers an enormous area. It's possible that, by sheer chance, we're seeing an unusual but not impossible temperature fluctuation. Some studies have suggested that while the cold spot is unusual, it might not be as improbable as we think. and could be explained by the normal variations in the CMB. However, this explanation leaves many scientists unsatisfied, as the size and scale of the cold spot still seem to push the boundaries of what we would expect from random chance. The mystery of the cosmic cold spot touches on some of the most fundamental questions in cosmology. If it's not just a fluke or a void, then what could it be? Could this strange cold patch of space be hinting at a deeper structure to the universe, one that we've only begun to glimpse? Some researchers have speculated that the cold spot might be related to dark matter or dark energy, the mysterious substances that make up the majority of the universe's mass and energy. If this region of space has an unusual concentration of dark matter or dark energy, it could explain the temperature anomaly. But dark matter and dark energy remain largely theoretical, and we still don't fully understand how they interact with the universe at large. The cold spot also raises larger philosophical questions. If the multiverse theory is correct, and the cold spot is indeed the result of a collision with another universe, what does that mean for our place in the cosmos? Are we just one of countless universes, each with its own history, rules, and possibilities? And if our universe can interact with others, could there be more signs of these collisions, waiting to be discovered? Or if the cold spot is a void, or some other unknown cosmic structure, what does that say about the fundamental nature of space and matter? Could there be regions of the universe where the laws of physics behave differently, or where matter is distributed in ways we don't yet understand? The faint young sun paradox. How did Earth stay warm? Around 4.5 billion years ago, the young Earth was already forming its oceans, landmasses, and atmosphere. During this early period, the sun was significantly dimmer than it is today, shining with about 70% of its current brightness. According to what we know about stars and their life cycles, a dimmer sun should have meant that Earth was much colder, perhaps even frozen over. Yet, geological evidence shows that early Earth had liquid water, rivers, and possibly oceans, with a climate warm enough to support the development of life. This contradiction between what we expect from a faint young sun and the reality of a warm early Earth creates a mystery known as the faint young sun paradox. This paradox presents a puzzle for scientists because, under the conditions expected from the sun's lower energy output, Earth should have been an icy, uninhabitable planet during its early history. Instead, it had an environment capable of fostering the emergence of life. The big question that arises is, how did Earth stay warm enough for liquid water and life to exist when the sun wasn't producing enough heat? One of the leading explanations for the faint young sun paradox is that early Earth's atmosphere was far more effective at trapping heat than it is today. Some scientists suggest that higher levels of greenhouse gases, such as carbon dioxide, CO2, and methane, CH4, could have compensated for the sun's reduced energy output. Greenhouse gases work by trapping heat within a planet's atmosphere, creating a warming effect, much like the glass of a greenhouse keeps heat from escaping. If early Earth's atmosphere had been rich in these gases, it might have retained enough heat to keep the planet warm and prevent the oceans from freezing. There is evidence to support this idea. Volcanic activity on early Earth would have released large amounts of carbon dioxide, while methane-producing microbes might have added to the greenhouse gas levels. Together, these gases could have created a thick, heat-trapping blanket in the atmosphere, helping the planet maintain temperatures suitable for liquid water and, eventually, life. But while the greenhouse gas theory is compelling, it doesn't fully solve the paradox. For one, it's still unclear exactly how much of these gases would have been present in the atmosphere at that time. Estimates vary widely, and it's difficult to reconcile the amounts needed with the geological record. It could also be that the Earth's albedo plays a role. This is a measure of how much sunlight is reflected back into space. A lower albedo means more sunlight is absorbed, warming the planet. If early Earth had fewer reflective surfaces, like ice and snow, it could have absorbed more of the sun's limited energy, helping to keep the planet warm. Additionally, the early oceans and a different composition of clouds could have played a role in trapping more heat. However, while changes in albedo could have contributed to the solution, they alone are unlikely to account for the significant difference in the Sun's energy output. Some scientists also propose that Earth's magnetic field could have been stronger during its early history, helping to protect the planet from solar winds and other cosmic forces that could have stripped away its atmosphere. A thicker atmosphere would have contributed to the greenhouse effect, further insulating the planet. But again, this theory only adds a piece to the puzzle. It doesn't fully resolve the paradox. The faint young sun. Paradox is not just a question about Earth's distant past, it has broader implications for our understanding of planetary habitability in general. If early Earth could remain warm with a much weaker sun, what does that say about the potential for life on other planets? Could planets orbiting weaker or dimmer stars still support life if they have the right atmospheric conditions? Solving this paradox could provide important clues in the search for habitable exoplanets. One of the most intriguing aspects of the faint young sun paradox is how it challenges our assumptions about the conditions necessary for life. Today, we think of life as needing a certain amount of sunlight to sustain a warm, stable climate. But early Earth shows us that life can emerge and thrive under very different conditions, possibly opening the door to a wider range of environments where life might exist. Understanding how early Earth stayed warm despite a faint sun could also help scientists refine their models for planets in distant star systems, expanding the search for potentially habitable worlds. There are even more radical ideas proposed to explain the paradox. Some have suggested that the early solar system might have experienced a period of heightened activity, with solar flares or other energetic events providing temporary bursts of additional warmth. While these ideas are less mainstream, they highlight the lengths to which scientists must go to try to solve such a persistent mystery. Then, there's the question of whether the Sun itself might have behaved differently during its early life. Could the young Sun have gone through periods of increased activity or fluctuations in its output that we haven't yet accounted for? Some researchers have explored the possibility that the Sun was more variable than we've thought, with short bursts of increased brightness. However, current models of stellar evolution suggest that while stars like the Sun do change over time, they follow fairly predictable patterns, and there's no strong evidence to suggest the Sun was significantly more active than expected during that time. In trying to solve the faint young sun paradox, scientists are continually faced with more questions than answers. Each possible explanation adds another piece to the puzzle, but no single theory has yet been able to account for all the evidence. This mystery challenges our understanding of both planetary climates and star formation, and it may hold the key to unlocking new insights about the conditions under which life can develop and thrive. What makes the faint young sun paradox so compelling is that it touches on the core of what makes Earth unique, and yet, at the same time, it forces us to reconsider how common those conditions might be elsewhere in the universe. If Earth could sustain life with a faint sun, then perhaps other planets, even those orbiting dimmer stars, might also harbor life, hidden away beneath protective atmospheres or in climates that we currently consider inhospitable. FRBs, the hidden signals of the universe. In the early 2000s, astronomers stumbled upon something unexpected and strange, a fleeting but powerful burst of radio waves from deep space. These signals, now known as fast radio bursts, FRBs, last only milliseconds but pack an extraordinary punch of energy. In that brief moment, an FRB can emit as much energy as the sun does in an entire day. The bursts are so intense that for a fraction of a second they can outshine entire galaxies. Yet they are incredibly elusive, making them one of the most mysterious and hotly debated phenomena in modern astronomy. Fast radio bursts come from far beyond our galaxy, originating from some of the most distant regions of the universe. What makes them so perplexing is their sheer power and the fact that they seem to appear out of nowhere. with no warning and no clear pattern. They flash for just a few milliseconds and then vanish, leaving no trace. Since their discovery, astronomers have detected hundreds of these bursts, but despite extensive study, their source remains speculative. The mystery surrounding FRBs lies not only in their fleeting nature, but also in the vast distances they travel. These bursts are believed to come from galaxies billions of light-years away, meaning they have traveled across the cosmos to reach us. The fact that such immense energy is carried across such vast distances, yet only lasts for the blink of an eye, makes it all the more baffling. What could produce such an event? And why do these bursts occur in such a short time frame? One of the first major clues about FRBs came when astronomers were able to pinpoint the location of one of these bursts back to its host galaxy. This discovery suggested that FRBs originate from outside our Milky Way and may be tied to highly energetic processes in distant galaxies. However, this still left many questions unanswered. Were they caused by exploding stars, collapsing black holes, or perhaps some other as yet unknown cosmic event? Some theories suggest that FRBs could be linked to neutron stars, super-dense remnants of dead stars that can have powerful magnetic fields. In particular, some scientists have pointed to a type of neutron star known as a magnetar, which has a magnetic field millions of times stronger than any magnet found on Earth. Magnetars are known to produce sudden bursts of energy, and some researchers believe they could be responsible for at least some FRBs. But even this explanation doesn't fully account for all the observations, and the source of most FRBs remains unidentified. What adds to the intrigue is that while most FRBs seem to happen only once, a few of them repeat. These repeating FRBs have allowed scientists to study them in greater detail, but they raise more questions than they answer. If some bursts repeat, while others do not, does that mean they are caused by different types of events? Or is there something about the repeating bursts that we don't yet understand? Given the mysterious nature of FRBs, it's perhaps no surprise that some have speculated that these bursts could be signals from extraterrestrial civilizations. After all, the idea of receiving a powerful, brief communication from another galaxy is the stuff of science fiction. Could FRBs be a form of cosmic communication, a signal sent out intentionally by intelligent beings from distant galaxies? It's an exciting idea, but most scientists are cautious about jumping to such conclusions. There's no concrete evidence to suggest that FRBs are anything other than a natural, albeit mysterious, phenomenon. Still, the possibility remains in the realm of speculation. If an advanced civilization wanted to send a signal across the universe, using high-powered bursts of energy might be one way to do it. The fact that FRBs are so powerful and can travel such vast distances lends a bit of weight to the idea. But so far, no clear pattern has emerged in the bursts that would suggest they are anything other than random. And while the idea of extraterrestrial communication is tantalizing, it's also worth noting that the universe is full of powerful forces and energetic events, many of which we still don't fully understand. Even if FRBs are not the work of intelligent civilizations, their existence points to something remarkable about the universe. Whatever is causing these bursts is incredibly energetic and must involve some of the most extreme conditions in space. The fact that we don't yet know what those conditions are makes the mystery even more profound. Are FRBs the result of cataclysmic cosmic events that we have yet to witness directly, or do they represent a new, previously unknown class of astronomical phenomena? The discovery of FRBs has opened up a new area of inquiry in astronomy, one that could lead to answers about some of the most powerful forces in the universe. If we can figure out what is producing these bursts, we might unlock new insights into the life cycle of stars, the behavior of black holes, or even the structure of galaxies themselves. The ongoing search for answers continues to push the boundaries of what we know. As more telescopes are trained on the sky, astronomers hope to catch more FRBs in real time, allowing for better analysis and understanding. Some of the most sensitive radio telescopes in the world are now dedicated to monitoring these bursts, and new detections are coming in regularly. Each new burst offers a potential clue, but also adds to the complexity of the puzzle. Pluto's underground ocean, a water world beneath the ice. In 2015, when NASA's New Horizons spacecraft made its historic flyby of Pluto, the distant icy world revealed itself to be far more complex than anyone had anticipated. Pluto, once considered the 9th planet in our solar system, before being reclassified as a dwarf planet, surprised scientists with its stunning landscapes, towering mountains, and smooth plains. But perhaps the most unexpected discovery was the evidence pointing to something even more astonishing: a possible liquid ocean hiding beneath Pluto's frozen surface. This revelation came as a shock. Pluto orbits far from the Sun, in a region of the solar system where temperatures drop to extremes, averaging around -375 degrees Fahrenheit, -225 degrees Celsius. At such cold temperatures, it seems impossible that liquid water could exist. Yet, data from New Horizons suggests that beneath Pluto's thick, icy crust, there may be a slushy liquid ocean that has remained unfrozen for billions of years. The idea that Pluto, a distant world in the frozen Kuiper belt, could harbor liquid water is puzzling. In our solar system, liquid water is typically found on planets and moons much closer to the Sun, where heat can prevent water from freezing solid. But Pluto is located so far from the Sun that it receives only a tiny fraction of the sunlight that reaches Earth. Its surface is covered with nitrogen, methane, and carbon monoxide ices. So how could there be an ocean of liquid water beneath all that ice? The key to this mystery might lie in the way Pluto's internal structure works. While the surface of Pluto is cold and frozen, scientists believe that heat generated within the dwarf planet itself could be playing a role in keeping the water below from freezing. One possible explanation is that radioactive decay in Pluto's core generates enough heat to maintain a subsurface ocean. Radioactive elements like uranium, thorium, and potassium could be slowly releasing heat as they decay, providing a constant, if faint, source of warmth. Another factor might be the insulating properties of Pluto's thick ice crust. The ice could act like a thermal blanket, trapping the heat generated by radioactive decay and preventing it from escaping into space. This trapped heat would then be enough to keep a layer of water below the ice from freezing completely. If this is the case, Pluto could have a hidden ocean hundreds of kilometers beneath its surface, kept warm not by the Sun, but by the planet's own internal processes. But the mystery of Pluto's underground ocean doesn't stop there. Some scientists have suggested that the ocean might not just be water. It could be mixed with other substances, like ammonia, which acts as an antifreeze. Ammonia lowers the freezing point of water, allowing it to remain liquid at much colder temperatures than pure water. If Pluto's ocean contains ammonia, it could explain how the water has stayed in a liquid state for so long, despite the freezing conditions on the surface. The possibility of a subsurface ocean on Pluto raises intriguing questions about the potential for life. On Earth, wherever we find liquid water, we tend to find life. Deep beneath the surface of our planet, in the dark, high-pressure environments of Earth's ocean floors, life thrives around hydrothermal vents, using chemical reactions rather than sunlight as a source of energy. Could similar conditions exist beneath Pluto's icy shell? While it's still too early to say whether life could exist on Pluto, the discovery of a potential underground ocean broadens our understanding of where life might be able to survive in the solar system. For years, scientists have focused on places like Mars, Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, as potential candidates for extraterrestrial life because they either have or are thought to have liquid water beneath their surfaces. Now, Pluto joins that list as another icy world where liquid water might be hiding, raising the exciting possibility that life could exist in places far colder and more remote than we ever thought possible. Pluto's possible underground ocean also invites comparisons to other distant icy worlds. For example, Triton, a moon of Neptune, is believed to have similar characteristics, with evidence suggesting that it too may harbor an ocean beneath its frozen crust. In fact, many of the moons of the outer planets, particularly those in the Kuiper belt, could have subsurface oceans, kept liquid by a combination of internal heat and insulating ice layers. If there is liquid water on Pluto, it means that the conditions necessary for water to remain unfrozen are more widespread than we previously understood. This opens up a whole new area of exploration for scientists looking to understand the potential habitability of distant, icy bodies in the outer solar system. It also forces us to reconsider our assumptions about where liquid water, and possibly life, might exist beyond Earth. But how can scientists be sure that there's an ocean beneath Pluto's surface? Much of the evidence comes from the strange geological features observed on Pluto's surface. For instance, Sputnik Planitia, a large, smooth plain on Pluto's surface, appears to have been shaped by internal forces, possibly indicating the presence of a subsurface ocean. The way Pluto's crust appears to have deformed and stretched in certain areas suggests that liquid water below could be pushing up against the ice, creating these unique surface features. Another clue comes from the way Pluto's rotation seems to be affected by the presence of Sputnik Planitia. The region appears to have shifted over time, possibly due to the weight of the ice sitting on top of a liquid ocean, which would allow the surface to float and drift slightly as the planet rotates. This kind of behavior is consistent with other icy worlds, like Europa and Enceladus, where subsurface oceans are believed to exist beneath their frozen exteriors. The discovery of a potential underground ocean on Pluto has reinvigorated scientific interest in the dwarf planet. Although the New Horizons mission provided an unprecedented glimpse into Pluto's surface, there's still much we don't know about what lies beneath. Future missions to Pluto could focus on gathering more data about its internal structure, potentially using advanced instruments to detect the telltale signs of a subsurface ocean. For now, Pluto remains one of the most fascinating objects in the solar system, a world that has defied expectations at every turn. The missing baryons, a cosmic hide-and-seek. Everything we see, the stars, planets, galaxies, and even ourselves, is made up of what scientists call baryonic matter. This is the ordinary matter that we interact with every day, consisting of protons, neutrons, and electrons. But there's a problem. When scientists calculate how much of this matter should exist in the universe, they find that a significant portion of it seems to be missing. By all accounts, roughly 30 to 40% of the universe's baryonic matter is unaccounted for, leading to a mystery that has baffled astronomers for decades. This mystery is known as the missing baryons problem, and it raises profound questions about our understanding of the universe. Baryons are expected to make up about 5% of the universe's total content, with the rest being composed of dark matter and dark energy. Yet when scientists tally up all the baryonic matter they can observe, stars, galaxies, gas clouds, and other visible objects, they find much less than expected. Where is the rest of it? This missing matter isn't dark matter or dark energy, which are different problems altogether. It's the ordinary, visible matter that should be there, but simply isn't. The hunt for the missing baryons has taken astronomers on a cosmic hide-and-seek, scouring the universe for clues. The first place to look, naturally, was within galaxies themselves, but even after accounting for all the stars, gas, and dust in galaxies, the numbers still didn't add up. Astronomers then turned their attention to intergalactic space, the vast expanses between galaxies, where much of the universe's matter is believed to reside. Yet even here, only a portion of the missing baryons have been found, leaving the rest still hiding in plain sight. What makes this so puzzling is that we know the missing baryons must be out there somewhere. The early universe, shortly after the Big Bang, was filled with a nearly uniform distribution of baryonic matter. We can see evidence of this in the cosmic microwave background, CMB, the faint afterglow of the Big Bang, which provides a detailed picture of the early universe's composition. According to these observations, the universe should contain much more baryonic matter than we currently observe. One promising explanation for the missing baryons lies in what's known as the warm-hot intergalactic medium, or WIM. The WIM is a vast diffuse network of gas that stretches between galaxies, thought to be heated to temperatures of millions of degrees by the formation of large-scale cosmic structures like galaxy clusters. This extremely hot gas emits radiation that is difficult to detect, especially in visible light, which may explain why much of the missing matter has remained hidden from view. Recent observations using X-ray telescopes have provided some evidence for the existence of this hot gas, suggesting that the WIM might account for a significant portion of the missing baryons. However, even with these discoveries, not all of the missing matter has been found. The search for the missing baryons also leads us to consider the possibility that we may be looking in the wrong places, or even with the wrong tools. The universe is vast, and much of it remains unexplored in detail. Advanced instruments like the Chandra X-ray Observatory and the Hubble Space Telescope have helped identify potential baryon-rich regions. But detecting and mapping this faint matter requires technologies and techniques that are still being developed. Perhaps future missions will uncover the hidden reservoirs of baryonic matter that have eluded us so far. There are even more speculative ideas that take the mystery into the realm of the unknown. Could the missing matter be hiding in dimensions beyond the three spatial dimensions we're familiar with? Some physicists have suggested that extra dimensions could exist, curled up in ways that we don't experience in our everyday lives. If baryonic matter was somehow interacting with or hidden within these extra dimensions, it might explain why we can't find it. This idea, while intriguing, remains highly theoretical and is far from being proven. The missing baryons problem also forces us to consider whether our understanding of how matter is distributed throughout the universe might be incomplete. Perhaps the missing matter is locked away in dark, isolated pockets of the cosmos, or perhaps it's been pushed to the fringes by powerful forces like dark energy, which is driving the expansion of the universe at an accelerating rate. Whatever the case may be, the fact that we can't find such a large portion of the universe's ordinary matter challenges our grasp of cosmic structures and the forces that shape them. What makes this search so fascinating is that it mirrors some of the oldest questions humans have asked about the universe. What is out there? How is it all connected? The missing baryons, though a problem rooted in modern cosmology, tap into this ancient curiosity. We've built telescopes that can peer billions of light years into the past. We've mapped galaxies and nebulae, yet something so fundamental, ordinary matter, remains hidden. For scientists, solving the mystery of the missing baryons is about more than just completing a cosmic inventory. It's about understanding the universe's history and evolution. Baryons are the building blocks of everything we know, and figuring out where they are and how they behave could reveal new insights into how galaxies formed, how they interact with each other, and even how life might have emerged on planets like Earth. The star that won't explode, Betelgeuse's uncertain fate. In the constellation of Orion, one star stands out as a cosmic giant with a fate that has captured the imagination of astronomers and stargazers alike. Betelgeuse, a massive red supergiant located about 600 light-years from Earth, is one of the brightest stars in the night sky. It's also nearing the end of its life, which means that, at some point, it will explode in a spectacular supernova. The problem is that no one knows exactly when this will happen. In cosmic terms, Betelgeuse's demise could be imminent, tomorrow, next week, or it could be 100,000 years away. For decades, Betelgeuse has fascinated astronomers because of its unpredictable behavior. Unlike many stars, which follow relatively stable life cycles, Betelgeuse is erratic. Its brightness fluctuates over time, and its outer layers pulsate as it expands and contracts. This is because Betelgeuse is in the final stages of its life as a star, burning through the last of its nuclear fuel. As a red supergiant, it has swollen to enormous proportions. If placed at the center of our solar system, its outer layers would reach beyond the orbit of Jupiter. Eventually, when it exhausts its remaining fuel, Betelgeuse's core will collapse under its own gravity, triggering a supernova explosion that will be visible from Earth. For now, though, Betelgeuse remains intact, defying expectations of its imminent explosion. In recent years, the star has surprised astronomers once again by dramatically dimming, sparking speculation that it might be on the verge of going supernova. In late 2019 and early 2020, Betelgeuse's brightness dropped by more than 25%, becoming noticeably dimmer to the naked eye. For a star of its size and age, such a dramatic change in brightness led some to believe that its final explosion could be imminent. But just as quickly as it dimmed, Betelgeuse returned to its usual brightness, leaving astronomers puzzled. This dimming event, dubbed the Great Dimming, was one of the most significant changes in Betelgeuse's behavior ever observed. It raised questions about whether the star was entering its final phase before exploding, or if something else was happening entirely. Scientists scrambled to study the star more closely, using telescopes from around the world to monitor its fluctuations. But despite the excitement and speculation, Betelgeuse did not explode. Instead, it returned to its normal brightness, and the mystery deepened. So why did Betelgeuse dim so dramatically, only to recover? One of the leading theories is that the dimming was caused by a massive cloud of dust that was expelled from the star's outer layers. Red supergiants like Betelgeuse are known for shedding material as they age, and it's possible that this material formed a dust cloud that temporarily blocked some of the star's light, making it appear dimmer from Earth. As the dust dispersed, or moved out of our line of sight, Betelgeuse's brightness returned to normal. Another theory suggests that the dimming could have been caused by changes within the star itself. Betelgeuse, like all red supergiants, experiences complex internal processes that can cause its outer layers to swell and contract. It's possible that a cooling of the star's surface, combined with these internal changes, caused the temporary dimming. However, this explanation doesn't account for all the details observed during the Great Dimming, and many questions remain. Whatever the cause, the fact that Betelgeuse continues to shine brightly has left scientists wondering just how much longer it can hold on. When it does eventually go supernova, the explosion will be one of the most spectacular events ever witnessed from Earth. For a brief period, Betelgeuse will outshine even the Moon, becoming visible in broad daylight. The light from the explosion will be so intense that it could last for weeks or even months, creating a rare celestial spectacle that has not been seen in recorded human history. Despite this, predicting exactly when Betelgeuse will explode remains impossible. Stars like Betelgeuse follow complex, sometimes chaotic life cycles that can be difficult to model accurately. While scientists have a good understanding of the basic stages a star goes through before going supernova, pinpointing the exact moment when the final collapse will occur is another matter entirely. In many ways, Betelgeuse is like a ticking time bomb, but one with a timer that could go off at any moment or not for thousands of years. The uncertainty surrounding Betelgeuse's fate only adds to its allure. The star has been a key feature of human stargazing for thousands of years, with ancient cultures tracking its movements and incorporating it into their myths and constellations. Its reddish hue and prominent position in the sky have made it a familiar sight for civilizations across the globe, from the ancient Egyptians to the Greeks. Now, in the modern era, Betelgeuse has become a focal point for scientific inquiry, as astronomers work to unravel the mysteries of its erratic behavior. If Betelgeuse's explosion is as spectacular as expected, it could also provide a rare opportunity for scientists to study the supernova process up close. Supernovas are responsible for creating many of the heavy elements found in the universe, including those that make up planets and even life itself. By studying Betelgeuse's eventual explosion, scientists could gain valuable insights into the mechanisms behind these powerful cosmic events and the role they play in shaping the universe. One of the most interesting twists in Betelgeuse's story is the possibility that the star is giving us subtle hints about its impending explosion. While the Great Dimming may not have been the final warning sign many had hoped for, it shows that Betelgeuse is far from stable. Could other signs be on the way? Will astronomers be able to detect small changes in the star's behavior that indicate the final stages of its life are approaching? Or will Betelgeuse surprise us all by holding on for thousands of years longer than expected? The missing stars of the Large Magellanic Cloud. The Large Magellanic Cloud, or LMC, is a galaxy just next door in cosmic terms, sitting about 160,000 light-years from Earth. It's visible from the southern hemisphere as a cloudy smudge in the night sky. But through a telescope, it reveals itself as a complex and vibrant galaxy filled with stars, nebulae, and clusters. The LMC is one of the closest galaxies to our own Milky Way, and because of this proximity, it has been studied in great detail by astronomers for centuries. However, despite this long history of observation, the LMC holds a mystery that continues to baffle scientists. A vast region within the galaxy where there should be stars, but instead, there are none. It's as though entire generations of stars have vanished, leaving behind a cosmic ghost town. Galaxies are bustling with star formation, a process that usually follows predictable patterns. As gas clouds collapse under their own gravity, they ignite nuclear fusion, giving birth to stars. Over time, stars form, live out their lives, and eventually die, only to be replaced by newer generations of stars. But in this particular part of the Large Magellanic Cloud, this natural cycle of star birth seems to have come to a standstill. There's a noticeable gap, a region where astronomers would expect to see a vibrant population of stars, yet there's almost nothing. It's a cosmic anomaly that has left astronomers scratching their heads. What makes this absence of stars so puzzling is that there's no clear reason why this region should be missing its stars. The rest of the LMC is brimming with activity, from young star clusters to swirling clouds of gas and dust that serve as nurseries for new stars. But this region, covering a significant portion of the galaxy, is eerily empty, as if something stopped the star formation process or removed the stars entirely. It's not just a small gap in the cosmic fabric, it's a massive area, one that should be rich with stars of various ages and sizes, like the rest of the galaxy. One of the first questions that arises is whether something prevented stars from forming in this part of the galaxy in the first place. Could the conditions in this region have been somehow unfavorable for star formation? To form stars, a galaxy needs cold gas, primarily hydrogen, that can collapse under gravity. If this gas was absent or disrupted in some way, it might explain the lack of stars. However, observations show that the region does contain gas, and in fact, the LMC is known for its active star formation in other areas, so the idea that this region simply lacked the material for stars seems unlikely. Another possibility is that something interfered with the star formation process, halting it before it could really begin. Galaxies are dynamic systems, constantly interacting with their surroundings. The LMC is no exception, as it is in orbit around the Milky Way and may have been influenced by its larger neighbor. Some scientists have proposed that tidal forces from the Milky Way could have disrupted the gas in this region of the LMC, preventing stars from forming. Alternatively, past interactions between the LMC and the nearby Small Magellanic Cloud, another dwarf galaxy, could have stripped the gas from this region, depriving it of the fuel needed for star formation. But while these ideas offer some explanation, they don't fully account for the scale of the missing stars, or why the rest of the galaxy continues to form stars without issue. An even stranger idea is that the stars may have formed and then somehow disappeared. This raises the question of whether some kind of cosmic catastrophe could have wiped out entire generations of stars. Could a massive event, such as a burst of supernova, have swept through this part of the galaxy, destroying the stars and leaving behind an empty region. Supernovae are incredibly powerful explosions that occur when massive stars reach the end of their lives, and they have the ability to disrupt entire star systems. A chain reaction of supernovae might have occurred, blowing away the remaining gas and even flinging stars out of the region entirely. But this too seems unlikely on the scale we're seeing in the LMC. The possibility that stars could simply vanish from a galaxy opens up other, more speculative questions. Could there be unknown cosmic processes at work that we don't yet understand? Some have even wondered if black holes, particularly the supermassive black hole that likely resides in the center of the LMC, could have played a role. Black holes are known for their ability to swallow matter, including stars, but it would take an extraordinary set of circumstances for a black hole to clear out such a large swath of a galaxy. And even then, we would expect to see evidence of the stars being torn apart, which is not the case here. The idea of a cosmic ghost town, an entire region of a galaxy missing its stars, raises philosophical questions about the nature of galaxies and the processes that shape them. What could cause such a large-scale disappearance of stars? Are these voids in star formation relics of an early stage in the universe's evolution? Or are they signs of unknown cosmic forces at play? Galaxies like the LMC are some of the oldest structures in the universe, formed billions of years ago from the same primordial material that created everything we see today. Could this missing region be a remnant of those early days, somehow preserved while the rest of the galaxy evolved? It's possible that the missing stars of the Large Magellanic Cloud are telling us something fundamental about the nature of galaxies and star formation, something we haven't yet fully grasped. Galaxies are vast, complex systems that operate on timescales far beyond human comprehension. The processes that govern them are often hidden from view, taking place over millions or even billions of years. This missing region in the LMC could be the result of forces that have been at work for eons, shaping the galaxy in ways that are still a mystery to us. The Hanny's Voorwerp, a giant glowing blob in space. In 2007, something strange appeared in the universe, discovered not by a seasoned astronomer, but by a Dutch schoolteacher named Hanny van Arkel. While participating in the Galaxy Zoo project, an online citizen science initiative that allows volunteers to classify galaxies from telescope images, Hanny came across a bizarre glowing green blob near the spiral galaxy IC 2497. This object didn't resemble any star, planet, or galaxy. In fact, it didn't match anything astronomers had seen before. It quickly became known as Hanny's Voorwerp, meaning Hanny's object in Dutch. But despite its name, the exact nature of this unusual celestial body remains one of the most intriguing mysteries in the universe. Hanny's Voorwerp is enormous, spanning nearly 16,000 light-years in diameter, roughly the size of an entire galaxy. Yet, it's not a galaxy at all. Instead, it appears to be a cloud of gas, glowing intensely with a brilliant green hue. But why? What could make this massive gas cloud light up in such a way? At first glance, the object seemed completely out of place in the orderly images of galaxies and stars. The strange glow, unlike anything astronomers had observed, demanded further investigation. One of the leading theories to explain Hanny's Voorwerp is that it is somehow connected to the galaxy IC 2497, located nearby. IC 2497 is home to a supermassive black hole at its center, and this may be the key to understanding the Voorwerp's strange glow. Black holes, particularly the supermassive ones found at the centers of galaxies, can have dramatic effects on their surroundings. As material is drawn toward the black hole, it forms an accretion disk, a spinning ring of gas and dust that heats up and releases intense energy, sometimes in the form of powerful radiation. This process can produce an extremely bright and energetic phenomenon known as an active galactic nucleus, AGN. Scientists believe that Hanny's Voorwerp might be a relic of one of these active galactic nuclei. They hypothesize that millions of years ago, The black hole in IC 2497 was actively feeding, emitting large amounts of radiation. This radiation could have blasted outward and illuminated the gas cloud that now appears as Hanny's Voorwerp. The glowing green light comes from ionized oxygen within the gas, which emits light at a very specific wavelength when it is energized by intense radiation. Essentially, the gas cloud was lit up by the black hole's energy, much like how a neon sign glows when an electric current runs through it. What makes Hanny's Voorwerp even more puzzling is that the black hole in IC 2497 appears to have since turned off. When astronomers observed the galaxy, they found no evidence that the black hole is still actively consuming material. Yet the Voorwerp continues to glow, even though the source of its energy seems to have disappeared. This suggests that we are witnessing a kind of cosmic afterglow. The radiation that once powered the Voorwerp is still lingering, causing the gas to remain visible long after the black hole's activity has ceased. But exactly how long this glow can persist is still unknown. The discovery of Hanny's Voorwerp has sparked new questions about the life cycles of galaxies and the role of black holes in shaping their environments. Black holes are often thought of as destructive forces, consuming everything that gets too close. But in reality, they are also capable of creating spectacular light shows and influencing vast regions of space, as seems to be the case with the Voorwerp. In this case, the black hole's radiation appears to have reached out across tens of thousands of light-years, igniting a distant gas cloud in the process. Yet even with this explanation, there are still many unanswered questions about Hanny's Voorwerp. For one, what caused the black hole in IC 2497 to become so active in the past, and why did it suddenly shut down? Black holes don't typically turn on and off like light switches. Changes in their activity can take millions of years. What we might be seeing in Hanny's Voorwerp is the result of a process that played out long ago, giving us a rare glimpse into a distant event. Another mystery is why there aren't more objects like Hanny's Voorwerp. If this glowing gas cloud was lit up by the radiation from an active black hole, we might expect to see similar objects in other parts of the universe. Yet so far, very few examples of such Voorwerpen have been found. This suggests that the circumstances leading to the creation of Hanny's Voorwerp might be rare, or that these objects fade too quickly for us to observe them in large numbers. Could Hanny's Voorwerp point to a new type of cosmic interaction, one that we don't yet fully understand? The object's sheer size and unusual glow challenge our assumptions about how galaxies and black holes interact. If black holes can have this kind of far-reaching impact, then there may be other unseen influences at work in galaxies throughout the universe. Some scientists have speculated that Hanny's Voorwerp might be part of a larger, more complex process that involves not only the black hole's energy, but also the surrounding galaxy's own dynamics, such as the movement of gas and the formation of stars. There's also the possibility that Hanny's Voorwerp could help us better understand the way energy travels through space. The light we see from the Voorwerp today has been traveling for millions of years, giving us a snapshot of a past event that is no longer happening. In a sense, we are looking at an echo of the past, preserved in the glowing gas of the Voorwerp. By studying objects like this, astronomers can piece together the history of galaxies and black holes, learning more about the events that shaped the universe long ago. Despite years of study, Hanny's Voorwerp remains an object of fascination and mystery. Its discovery has led to new avenues of research, as astronomers search for other objects like it and try to understand the mechanisms that caused it to glow. In the years since its discovery, scientists have identified a few other similar objects, now known as Voorwerpjes, or little Voorwerps, scattered across the sky. But none are quite as large or as prominent as the original Hanny's Voorwerp. Venus's phosphine gas, a sign of life. In 2020, a discovery was made that reignited one of the most profound questions in science. Could there be life beyond Earth? The unexpected finding came from a planet long thought to be one of the least likely places for life to exist, Venus. Known for its scorching surface temperatures, which reach around 900 degrees Fahrenheit, 475 degrees Celsius, and its thick toxic atmosphere composed primarily of carbon dioxide, Venus has always been considered inhospitable to life as we know it. But the detection of phosphine gas in the upper clouds of Venus changed everything, suggesting that even the most unlikely places might hold the potential for life. Phosphine is a chemical compound made up of one phosphorus atom and 3 hydrogen atoms. On Earth, phosphine is known to be produced through both industrial processes and biological activity, particularly by anaerobic microorganisms, microbes that thrive in oxygen-free environments. In fact, one of the key ways phosphine is found on Earth is in places like swamps, marshes, and even the guts of certain animals, where these microbes break down organic matter. Because phosphine is so strongly associated with life on Earth, its detection in the clouds of Venus sent shockwaves through the scientific community. What made the discovery even more intriguing was the location of the phosphine. Venus's surface is an inferno, hot enough to melt lead, and its atmosphere is dominated by sulfuric acid clouds that rain down corrosive droplets. However, at higher altitudes, between 30 and 40 miles above the surface, the conditions become much more temperate, with temperatures around 86 degrees Fahrenheit, 30 degrees Celsius, and pressures similar to those found on Earth. It is in this relatively cooler, more hospitable region of the atmosphere where the phosphine was detected, leading to speculation that life could potentially exist in these clouds. The idea of life on Venus, once considered outlandish, suddenly seemed possible. If microbes were producing phosphine on Earth, could something similar be happening in Venus's atmosphere? Could there be microscopic life forms adapted to the harsh conditions, living in the cloud layers above the planet's inhospitable surface? These questions ignited debates among scientists, as the implications of such a discovery would be nothing short of revolutionary. Finding life on Venus would suggest that life is far more common in the universe than we previously thought, and that it might arise in environments vastly different from Earth's. However, the discovery of phosphine on Venus is far from a smoking gun for life. While phosphine is produced by biological processes on Earth, it can also be created through chemical reactions. This has led some scientists to caution against jumping to conclusions, pointing out that we don't fully understand all the chemical processes that might occur in Venus's atmosphere. Venus is a planet with unique and extreme conditions, and it's possible that the phosphine detected there could be the result of some unknown chemical reaction happening in the atmosphere, rather than a sign of microbial life. One of the challenges in interpreting the phosphine discovery is that we still don't know all the details about Venus's atmosphere. While phosphine on Earth is a clear indicator of biological activity, the conditions on Venus are so different that it's possible some other process, one we haven't yet identified, is responsible for the gas. For instance, lightning strikes, volcanic activity, or chemical reactions driven by sunlight could potentially produce phosphine. But even with these possibilities in mind, no known non-biological process can easily explain the high levels of phosphine detected in Venus's atmosphere, which keeps the door open to the tantalizing possibility of life. The debate over the phosphine discovery has sparked a flurry of research and discussion within the scientific community. Some teams are focusing on better understanding the chemical composition of Venus's atmosphere, while others are exploring the possibility of sending new missions to the planet to gather more data. Venus has long been overlooked in the search for extraterrestrial life, with much of the focus on Mars or the icy moons of Jupiter and Saturn. But the phosphine discovery has shifted attention back to Venus, highlighting the need for more exploration of this mysterious world. One of the biggest challenges in confirming the presence of life on Venus is the difficulty of studying the planet up close. Venus's thick clouds and harsh atmospheric conditions make it one of the most challenging planets to explore. While there have been missions to Venus in the past, such as NASA's Pioneer Venus missions and the Soviet Union's Venera landers, no spacecraft has visited Venus in recent decades, with the specific goal of searching for signs of life. Now, however, with the Phosphine discovery raising the stakes, plans for new missions to Venus are being discussed. NASA has announced the Da Vinci Plus and Veritas missions, both aimed at studying Venus's atmosphere and geology in greater detail. These missions will help scientists gather more data on the chemical processes happening in Venus's clouds, and potentially provide answers about the origins of the phosphine gas. Meanwhile, the European Space Agency's Envision mission, scheduled for the 2030s, will also play a key role in exploring Venus's surface and atmosphere. The excitement surrounding Venus's phosphine discovery goes beyond just the possibility of finding life. It also challenges our assumptions about where life could exist in the universe. For a long time, the search for life beyond Earth has focused on planets and moons with liquid water, Mars, Europa, and Enceladus, for example. But the discovery of phosphine on Venus suggests that life might arise in places that seem inhospitable by Earth's standards. If life can survive in the acidic, sulfur-laden clouds of Venus, what other unexpected environments might harbor life? At the same time, this discovery forces us to reconsider what signs of life might look like. Traditionally, scientists have focused on finding water or oxygen as key indicators of life. But phosphine shows that there might be other, less obvious markers to look for. The search for life beyond Earth is evolving as new tools and discoveries push the boundaries of what we consider to be a habitable environment. Despite the ongoing debate, one thing is clear. The discovery of phosphine on Venus has brought the planet back into the spotlight. It has reminded us that the universe is full of surprises, and that even the most hostile environments might harbor life in some form. As scientists continue to investigate this mystery, the possibility that we are not alone in the universe becomes just a little more real. The X-ray ghosts, a glimpse of ancient stars. In 2014, astronomers stumbled upon a puzzling discovery that sent ripples through the scientific community: mysterious X-ray signals coming from two galaxy clusters. These signals, unlike any radiation previously detected, didn't fit the patterns of known X-ray sources. Galaxy clusters, enormous structures made up of thousands of galaxies bound together by gravity, are hotbeds of energetic activity. But these X-rays were different. They didn't align with the expected emissions from hot gas, stars, or black holes that typically dominate such regions. Instead, they hinted at something much more elusive and mysterious. Something that could even hold the key to unlocking one of the greatest enigmas in astrophysics. What caught the attention of scientists was that the X-ray signals didn't match any known phenomenon in space. The radiation had a unique signature, one that didn't conform to the usual sources astronomers are familiar with, like supernovae, black hole accretion disks, or stellar remnants. This led to speculation that the X-ray signals might be something entirely new, a glimpse of ancient unseen forces at work, possibly linked to dark matter, the invisible substance that makes up most of the universe's mass but has never been directly detected. Dark matter, though it doesn't emit, absorb, or reflect light, exerts gravitational effects on visible matter. We know it exists because galaxies rotate faster than they should, based on the amount of visible matter they contain. However, direct evidence of what dark matter is made of has remained elusive for decades. The idea that these mysterious X-ray signals could be tied to dark matter offered a tantalizing possibility. What if these X-rays were coming from decaying dark matter particles, finally offering the first tangible glimpse of this invisible substance? One theory suggests that the X-rays might be produced by sterile neutrinos, a hypothetical type of particle that could make up dark matter. Sterile neutrinos, if they exist, would be an extension of the known neutrinos, ghostly particles that pass through matter almost undetected. Unlike regular neutrinos, sterile neutrinos wouldn't interact with ordinary matter, making them a prime candidate for dark matter. According to this theory, the X-rays detected in the galaxy clusters might be the result of sterile neutrinos decaying over time, releasing energy in the form of radiation that we can now detect. If these X-ray signals are indeed linked to dark matter, it would be a breakthrough of immense proportions. For years, scientists have been searching for a way to directly detect dark matter, and these X-ray ghosts could represent the first direct evidence of its existence. It would not only help confirm the nature of dark matter, but also revolutionize our understanding of how the universe is structured. Dark matter plays a crucial role in the formation and evolution of galaxies, and solving the mystery of its composition could reshape our view of the cosmos. However, the idea that these X-rays are the result of dark matter decay is still highly speculative. While the sterile neutrino theory is intriguing, there are other possible explanations for the X-ray signals, and scientists have yet to reach a consensus. Some researchers argue that the X-rays could be coming from much more familiar, albeit ancient sources, stars that have long since died, sending out their final echoes across the universe. Stars go through different life cycles, and when massive stars die, they often leave behind remnants like neutron stars or black holes. These stellar remnants can continue to emit radiation long after the stars themselves have disappeared. One possibility is that the X-rays detected in the galaxy clusters could be the final emissions from stars that died billions of years ago. These stars, now long dead, may be sending out their last pulses of energy in the form of X-ray radiation that has traveled across space and time to reach us. If this is the case, the X-ray signals would represent a kind of cosmic fossil record, traces of stars that existed in the early universe, whose light has been redshifted and transformed as it crossed vast distances. These X-ray ghosts could be the remnants of the first generation of stars, known as population 3 stars, which formed shortly after the Big Bang. These ancient stars, much larger and more massive than the stars we see today, burned through their fuel quickly and died in dramatic supernova explosions. While their light may have faded, the energy they released might still be echoing across the cosmos, visible now as faint X-ray signals. The idea that the X-ray ghosts could be linked to dead stars is both haunting and fascinating. It would mean that we are observing the final vestiges of stars that lived and died billions of years ago, their energy now lingering as faint whispers in the universe. These X-rays, if they are indeed coming from long-dead stars, could help scientists learn more about the earliest epochs of the universe and the life cycles of the first stars that helped shape the galaxies we see today. Still, neither explanation, dark matter decay or ancient stars, can fully account for all the details of the X-ray signals. The mystery remains open, and astronomers are working to gather more data to better understand the source of these strange X-rays. One of the challenges is that the X-ray emissions are incredibly faint, making them difficult to study in detail. Moreover, the signals have only been detected in a limited number of galaxy clusters, raising the question of whether they are unique to certain regions of space or if they are a more widespread phenomenon that we simply haven't yet observed elsewhere. If future observations confirm that the X-ray ghosts are tied to dark matter, it would mark a major milestone in cosmology. The nature of dark matter has been one of the most elusive questions in astrophysics, and finding direct evidence of its existence would help solve one of the universe's greatest mysteries. It would also open up new avenues for research, as scientists would be able to study dark matter in ways that were previously impossible, potentially leading to new discoveries about the structure and evolution of galaxies. On the other hand, if the X-rays turn out to be the remnants of ancient stars, they would still provide valuable insights into the history of the universe. Understanding the final stages of these early stars and the energy they release could help astronomers piece together a more complete picture of how galaxies and stars evolved over time. These X-ray ghosts would serve as a cosmic time capsule, offering a glimpse into the distant past and the processes that shape the universe we see today. A squashed dwarf planet. In the far reaches of our solar system, beyond the orbit of Neptune, lies a small but peculiar world named Haumea. Classified as a dwarf planet, Haumea is unlike any other in its category, not just because of its distant location in the Kuiper Belt, but because of its incredibly strange, elongated shape. While most planets and moons in the solar system are spherical, Haumea looks more like a football, stretched out along its axis. Adding to the mystery, Haumea spins at a breakneck speed, completing one full rotation every 4 hours, one of the fastest rotations of any known object in the solar system. Together, these traits make Haumea a fascinating and puzzling object for scientists studying the outer solar system. Most planets and moons are round, a result of gravity pulling matter inward equally from all directions. The force of gravity works to create a sphere, the shape that allows an object to minimize its surface area and distribute gravitational forces evenly. But Haumea defies this norm. Its rapid spin has deformed it, stretching it into an oblong shape, almost as if it had been pulled at both ends. The question is, how did Haumea end up this way? The dwarf planet's fast spin is a crucial part of the puzzle. Haumea's rotation speed is so extreme that it's reshaped the dwarf planet, stretching it along its equator. While some celestial objects, like Jupiter and Saturn, also exhibit slight equatorial bulges due to their fast rotations, Haumea's case is far more dramatic. Its elongated shape indicates that something unusual must have happened to give it such a rapid spin. But what? One of the leading theories is that Haumea's strange shape and fast rotation are the result of a massive collision in its past. Collisions between objects in the Kuiper Belt are not unheard of. In this distant icy region of the solar system, where dwarf planets like Haumea reside, there is a swarm of smaller objects, leftover building blocks from the early formation of the solar system. It's possible that billions of years ago, Haumea was struck by another large object, a collision so violent that it set the dwarf planet spinning at an incredibly high speed. This collision theory is supported by the fact that Haumea has 2 small moons, Haiyaka and Namaka, which may be remnants of the debris created by such an impact. The moons orbit Haumea, and their existence suggests that the impact not only spun up the dwarf planet, but also ejected enough material to form these satellites. But while this explanation fits with Haumea's rapid spin, it doesn't fully account for the dwarf planet's extreme shape. Haumea's elongated form is so pronounced that even a massive impact may not be enough to explain how it became so deformed. Adding to the mystery is the fact that Haumea has a unique surface composition. The dwarf planet is covered in crystalline water ice, which is unusual for an object so far from the Sun. Crystalline ice forms at warmer temperatures and is not typically stable in the cold reaches of the Kuiper Belt, where temperatures drop to hundreds of degrees below freezing. The presence of this ice suggests that Haumea has undergone significant changes in its past, perhaps as a result of tidal forces or internal heating. Could these forces have played a role in shaping Haumea's odd form? Another intriguing feature of Haumea is its ring. In 2017, astronomers discovered that the dwarf planet has a thin ring of particles orbiting it, similar to the rings of Saturn, though much smaller and fainter. The discovery of a ring around Haumea was unexpected and adds yet another layer of complexity to the dwarf planet's story. Rings around planets and moons typically form from debris left over after collisions, or from material ejected by volcanic or tectonic activity. Haumea's ring might be another piece of evidence that points to a violent collision in its past, or it could be related to the dwarf planet's rapid rotation, which might be causing material to spin off from its surface and form the ring. The combination of Haumea's fast spin, elongated shape, moons and ring makes it one of the most enigmatic objects in the Kuiper Belt. Despite these unusual features, there's still much we don't know about Haumea. For instance, scientists are still trying to figure out how the dwarf planet's spin has remained so fast for billions of years. Over time, the gravitational forces exerted by the Sun, nearby planets, and Haumea's moons should have gradually slowed its rotation, yet Haumea continues to spin at a remarkable pace. Is there something about Haumea's internal structure or history that has allowed it to maintain this rapid spin for so long? One possibility is that Haumea is not as solid as it appears. If the dwarf planet has a more fluid interior, it could help explain how it has managed to keep spinning so quickly. A liquid or partially molten interior might allow Haumea to redistribute its mass in a way that supports its fast rotation. Alternatively, Haumea might have a very dense core surrounded by a thinner, icy crust. This kind of internal structure could also contribute to the dwarf planet's stability, allowing it to maintain its rapid spin without breaking apart. Haumea's moons, Hi'iaka and Namaka, also raise questions about the dwarf planet's past. Both moons orbit Haumea at different distances, with Hi'iaka being much farther out than Namaka. The moon's orbits are thought to be related to Haumea's spin, and their formation may hold clues to the violent history that shaped the dwarf planet. If Haumea was indeed struck by another large object, the resulting debris could have coalesced to form the moons. Studying their orbits and compositions could help astronomers piece together the timeline of Haumea's formation and its evolution over billions of years. Despite being one of the most intriguing objects in the solar system, Haumea remains difficult to study due to its distance from Earth. At roughly 4.5 billion miles away, Haumea is far beyond the reach of most current space missions. However, advancements in telescopic technology have allowed astronomers to observe the dwarf planet in more detail, and future missions to the Kuiper Belt may provide even more insights into Haumea's strange characteristics. One such mission could be similar to NASA's New Horizons, which famously flew by Pluto in 2015 and provided unprecedented close-up images of that distant world. A mission to Haumea would offer the chance to study its surface, moons, and ring up close, revealing the processes that shaped this squashed, rapidly spinning dwarf planet. Such a mission could also answer lingering questions about Haumea's interior structure and whether it holds any secrets about the early solar system. The loneliness of the supervoid. In the vast expanse of the universe, where galaxies and stars are spread out across incomprehensible distances, there exist regions that seem almost hauntingly empty. These regions, known as supervoids, are among the largest known structures in the cosmos, yet they contain almost nothing. Stretching across hundreds of millions of light years, supervoids are immense stretches of space where matter, whether galaxies, stars, or even gas, appears to be nearly absent. In a universe filled with so much light and energy, these voids present a profound and mysterious contrast, raising fundamental questions about the structure and evolution of the cosmos. Supervoids were first discovered through the mapping of large-scale structures in the universe. As astronomers surveyed the distribution of galaxies, they found that galaxies are not evenly spread out like dots on a grid. Instead, they tend to form clusters and filaments, connected like strands of a cosmic web, with vast empty spaces between them. These empty spaces are the voids, and while voids of various sizes are common throughout the universe, supervoids are in a league of their own. They are the largest known voids, spanning hundreds of millions of light years, and they are almost completely devoid of matter. What makes these supervoids so mysterious is their sheer size and emptiness. The universe is 13.8 billion years old, and in that time, matter has spread out, forming stars, galaxies, and clusters. But supervoids seem to defy this distribution, creating regions where matter is conspicuously absent. How did these vast emptinesses form in a universe that is otherwise full of cosmic matter? And what could have caused these regions to be so barren? One of the leading theories for the formation of supervoids is tied to the early history of the universe. In the moments following the Big Bang, the universe was a hot, dense, and nearly uniform soup of particles. Over time, slight variations in the density of matter began to form, leading to the eventual clumping of matter that would become galaxies and clusters. These clumps of matter were drawn together by gravity, while other regions, where there was less matter to begin with, became the empty spaces we now know as voids. Supervoids, according to this theory, are the result of these early differences in matter distribution being amplified over billions of years. In areas where there was less matter in the early universe, gravity couldn't pull as much material together to form galaxies or stars. As the universe expanded, these empty regions grew larger, creating the supervoids we observe today. But even with this explanation, supervoids remain an enigma. The scale of these voids is staggering, and their existence forces us to question whether our understanding of the universe's evolution is complete. Could there be unknown forces or processes that shaped these vast regions of emptiness? Are supervoids simply the natural result of the universe's expansion? Or do they represent something more profound? Perhaps even a byproduct of cosmic events we don't yet understand. Some researchers have speculated that supervoids might be linked to dark energy, the mysterious force that is driving the accelerated expansion of the universe. Dark energy remains one of the biggest mysteries in cosmology, and some theories suggest that it could have played a role in the formation of supervoids by preventing matter from collapsing into these regions. If dark energy is indeed connected to the supervoids, then studying these immense empty spaces could provide new insights into the nature of this elusive force and its impact on the universe. It's also possible that supervoids could be connected to the multiverse theory. This speculative idea suggests that our universe may be just one of many, each with its own unique properties and physical laws. In this scenario, supervoids could be the result of interactions between our universe and others, perhaps created by collisions or the gravitational influence of neighboring universes. While this idea remains firmly in the realm of speculation, it highlights just how little we still know about the true nature of the universe and its largest structures. For those who study supervoids, these empty regions are not simply voids of matter, they are also voids of information. In a universe that is otherwise rich with structure, energy, and motion, these lonely regions offer only silence. Observing a supervoid is like peering into a cosmic desert, where the usual markers of existence, stars, galaxies, light, are almost entirely absent. Yet, for all their emptiness, supervoids have much to teach us. By studying them, scientists hope to uncover new clues about the fundamental forces that shape the cosmos, the distribution of dark matter and dark energy, and the nature of the universe's large-scale structure. One of the most famous supervoids is the Eridanus supervoid, a massive region of space stretching over 1 billion light-years across. Located in the direction of the Eridanus constellation, this supervoid is not only enormous, but also associated with another cosmic oddity, the cold spot in the cosmic microwave background, CMB. The CMB is the faint radiation left over from the Big Bang, and while it is mostly uniform, the cold spot stands out as an unusually cool region. Some scientists have suggested that the Eridanus supervoid could be responsible for the cold spot, potentially influencing the radiation passing through it. However, this connection remains a subject of ongoing research and debate, adding yet another layer of mystery to these vast, empty regions. The supermassive black hole that shouldn't exist. In 2019, astronomers made a discovery that defied everything we thought we understood about black holes and the early universe. They found a supermassive black hole named J03131806, lurking in a galaxy that existed just 700 million years after the Big Bang, a period when the universe was still in its infancy. What's more, this black hole is enormous, with a mass 1.6 billion times greater than that of our Sun. For a black hole of such size to exist in the early universe challenges our fundamental understanding of how black holes form and grow. Based on current models, there simply shouldn't have been enough time for J03131806 to reach such a colossal size. Yet, there it is, out in the distant cosmos, growing faster and larger than anything we've observed before. The discovery of J03131806 raises a crucial question. How could this black hole have grown so quickly in such a short period of time? According to our best theories, black holes form when massive stars collapse under their own gravity at the end of their life cycles. Over time, these stellar black holes can grow larger by accumulating gas and dust from their surroundings, or by merging with other black holes. But this process takes time, millions, if not billions of years. The universe itself is only about 13.8 billion years old, and the discovery of J03131806 suggests that just 700 million years after the Big Bang, something far more dramatic was happening. What makes J03131806 even more perplexing is that it appears to be growing at an extraordinary rate. Black holes grow by pulling in matter, a process called accretion, where gas and dust swirl around the black hole and eventually fall into it. This accretion process releases enormous amounts of energy, often seen as bright quasars, which are among the brightest objects in the universe. J03131806 is associated with such a quasar, and its brightness indicates that the black hole is actively consuming vast amounts of material. However, even accounting for its rapid growth, the black hole's sheer size so early in cosmic history doesn't align with what we currently know about black hole evolution. According to the models, a black hole could theoretically form from the collapse of a massive star and then slowly grow larger over billions of years. But for J03131806 to reach 1.6 billion solar masses in such a short time, it would have needed a head start. One possibility is that this black hole didn't form from the collapse of a single star, but from the direct collapse of an enormous gas cloud in the early universe. This process, known as direct collapse black hole formation, is a theoretical model that suggests some black holes might have formed much more quickly than others, bypassing the stellar phase entirely. In this scenario, an enormous cloud of hydrogen gas, perhaps 100,000 times the mass of the Sun, could have collapsed directly into a black hole without first forming a star. This idea of a direct collapse black hole could help explain J03131806, but it still doesn't account for everything. Even if the black hole had formed from such a collapse, it would still need to grow at an extraordinary rate to reach its current size so early in the universe's history. The rate at which a black hole can grow is limited by what's known as the Eddington limit, a balance between the force of gravity pulling material in and the radiation pressure pushing it away. If a black hole tries to consume too much material too quickly, the radiation it emits will push the material away, slowing down the growth. Yet somehow, J03131806 seems to have bypassed this limit, growing far faster than what the Eddington limit should allow. The existence of this black hole challenges the very foundations of how we think black holes form and evolve. If J03131806 can exist in the early universe, then perhaps there are other processes at work that we haven't yet discovered. Could there be unknown mechanisms that allow black holes to grow more quickly than we thought? Or have we misunderstood the conditions of the early universe itself, failing to account for how gas and matter interacted in those first few 100 million years after the Big Bang? Another possibility is that J03131806 could have formed from the merger of multiple smaller black holes early in the universe's history. Black hole mergers are now well documented thanks to the detection of gravitational waves, ripples in space-time caused by massive objects like black holes colliding. It's possible that in the chaotic early universe, smaller black holes merged more frequently, rapidly growing into larger and larger black holes. However, even with this scenario, the timing remains problematic. There simply wouldn't have been enough time for J03131806 to grow to its current size through mergers alone. The discovery of this supermassive black hole has far-reaching implications for our understanding of the early universe. One of the main puzzles it raises is how galaxies themselves formed and evolved. In modern galaxies, supermassive black holes like the one at the center of the Milky Way are thought to play a key role in regulating the formation of stars and the distribution of gas and dust. But in the early universe, these black holes would have been even more influential, potentially shaping the formation of the first galaxies. If J03131806 existed just 700 million years after the Big Bang, it might mean that supermassive black holes played an even more significant role in galaxy formation than we previously thought. As astronomers continue to study J03131806, they hope to gain more insights into how this black hole formed and grew so quickly. Future telescopes, such as the James Webb Space Telescope, will allow scientists to peer even deeper into the early universe, providing more detailed observations of this black hole and others like it. These observations could help us refine our models of black hole growth and reveal new clues about the processes that shaped the universe in its earliest days. For now, J03131806 remains an enigma, a black hole that shouldn't exist according to the rules we thought governed the universe. Its discovery has forced scientists to rethink their understanding of how black holes form, grow, and interact with their surroundings. Whether through direct collapse, mergers, or some other unknown process, the formation of J03131806 challenges everything we thought we knew about the early universe and its most mysterious objects. I hope you enjoyed this video. If you did, feel free to subscribe. Thank you for watching. The odd behavior of SN 1987A. In the year 1987, a star explosion shook the cosmos, revealing itself to Earth as supernova SN 1987A. Located in the Large Magellanic Cloud, a small galaxy near our own, this supernova was remarkable not only for its brightness but also for its puzzling behavior. When a star goes supernova, we expect to see a particular set of after effects based on well-established theories. Yet SN 1987A has defied these expectations in several key ways. The initial explosion was spectacular and highly visible from Earth, providing astronomers with a rare opportunity to study a supernova in real time. The after effects of SN 1987A, however, have raised more questions than answers. The supernova left behind an intricate structure of expanding debris, including a distinctive ring of gas surrounding a central, still luminous core. This configuration has proven to be particularly intriguing. One of the most striking aspects of SN 1987A's aftermath is the distribution of its debris. According to theoretical models, we should see a more uniform distribution of material ejected by the explosion. Instead, SN 1987A's debris is arranged in a surprisingly asymmetrical manner. This includes the well-known ring of material surrounding the core, which was initially thought to be a byproduct of the explosion. The ring's presence and its specific alignment with the core have raised questions about how the supernova's shock waves interacted with the surrounding gas. The central core of SN 1987A, which was expected to cool down and fade over time, has shown unusual activity. Instead of gradually dimming as anticipated, it has maintained a surprising level of brightness. This behavior has led scientists to reconsider their models of supernova remnants. One possibility is that the core is interacting with a dense surrounding cloud of gas, which could be affecting its luminosity and thermal evolution. Further complicating matters is the observation that SN 1987A's light curves, graphs depicting how the brightness of the supernova changes over time, don't match the standard patterns seen in other supernovae. These discrepancies suggest that either our theoretical models are incomplete or that there are unique factors influencing SN 1987A. This could involve the supernova's progenitor star, its pre-explosion environment, or the dynamics of the explosion itself. The asymmetry observed in SN 1987A's debris is also significant. Typically, supernovae create a roughly spherical explosion, distributing material evenly in all directions. However, SN 1987A's explosion appears to have created a more irregular pattern, with more material being expelled in certain directions. This could be a result of the interaction between the supernova's shock waves and the surrounding environment, which might have included pre-existing gas clouds or magnetic fields. Astronomers have also noted peculiarities in the way SN 1987A's debris is cooling and emitting light. The supernova's afterglow, which should theoretically follow a predictable cooling curve, has instead exhibited unexpected fluctuations. These changes could be caused by interactions with the surrounding interstellar medium or by internal processes within the supernova's expanding shell. The behavior of SN 1987 challenges our understanding of supernova physics and stellar explosions. Traditional models rely on certain assumptions about how stars explode and how their remnants evolve. SN 1987A's unique features suggest that there may be more complexity involved than previously thought. For instance, the supernova's interaction with its environment could be more influential than the explosion itself. This interaction could affect how the debris is distributed and how the supernova remnant evolves over time. Additionally, the unexpected characteristics of SN 1987A highlight the limitations of our current theoretical models. While they provide a framework for understanding supernovae, they may not account for all the variables at play in real-world scenarios. This realization is crucial for advancing our knowledge of stellar explosions and the life cycle of massive stars. The mysterious white dwarfs in Omega Centauri. The Omega Centauri star cluster, a sprawling collection of stars located about 15,800 light-years from Earth, has long been a treasure trove for astronomers studying the life cycle of stars. Among its many intriguing features are its white dwarfs, dead remnants of stars that have exhausted their nuclear fuel and collapsed into incredibly dense objects. These white dwarfs are of particular interest due to their unusual mass distributions and their enigmatic origins. White dwarfs are typically the end state for stars that were once similar in size to the Sun. After exhausting their nuclear fuel, these stars shed their outer layers, leaving behind a hot core that eventually cools and dims over time. In most star clusters, white dwarfs follow a predictable range of masses, dictated by the initial mass of the stars that became them and the processes they underwent in their final stages. However, the white dwarfs in Omega Centauri present a curious anomaly. The first clue that something was amiss came from observations showing a broader range of white dwarf masses than expected. In a typical star cluster, white dwarfs are found within a narrow mass range, reflecting a relatively uniform process of stellar evolution. Yet, Omega Centauri's white dwarfs show a significant spread in mass, suggesting that something unusual might be influencing their formation or evolution. This disparity in mass distribution raises questions about the origins of these white dwarfs. In Omega Centauri, it's possible that a large number of white dwarfs originated from binary star systems, where two stars orbit each other closely. When one of these stars evolved into a white dwarf, it might have pulled material from its companion, altering its mass. Alternatively, interactions between stars in dense clusters can lead to the formation of white dwarfs with unusual properties. The high stellar density in Omega Centauri could result in more frequent stellar collisions or exchanges of material, leading to a wider variety of white dwarf masses. The range of white dwarf masses observed in Omega Centauri also suggests that the cluster might have experienced a series of complex stellar evolutionary processes. In some cases, it's thought that white dwarfs in such clusters could be the result of interactions between stars that caused them to evolve in a non-standard manner. For instance, the cluster's dense environment might lead to more frequent interactions, including the merging of white dwarfs or the capture of white dwarfs by more massive stars. These white dwarfs also exhibit peculiarities in their chemical compositions, which could provide further clues about their origins. Observations have revealed that some of Omega Centauri's white dwarfs have unusual abundances of certain elements, suggesting that their progenitor stars may have undergone atypical chemical processes. This could be a sign that the stars that became these white dwarfs were part of complex binary systems, or that they experienced significant mass transfer events before becoming white dwarfs. The presence of these unusual white dwarfs in Omega Centauri challenges our understanding of stellar evolution. Traditionally, models of stellar evolution assume that white dwarfs form in a relatively uniform way, reflecting the properties of their progenitor stars. However, the diverse mass distribution and unusual chemical compositions observed in Omega Centauri indicate that the processes at play might be more complex and variable than previously thought. One intriguing hypothesis is that Omega Centauri, being a globular cluster, might have gone through a period of intense star formation early in its history. This could have led to a range of stellar masses and types, including the formation of white dwarfs with a variety of properties. The cluster's age and the subsequent interactions among its stars could have influenced the characteristics of its white dwarfs, leading to the observed anomalies. Another possible explanation is that Omega Centauri's white dwarfs are the result of multiple generations of star formation. In this scenario, the cluster would have experienced a series of star formation and evolution cycles, with different generations of stars contributing to the white dwarf population. This process could account for the wide range of masses and chemical compositions observed among the white dwarfs. The study of white dwarfs in Omega Centauri provides valuable insights into the life cycles of stars and the dynamics of star clusters. By examining these unusual remnants, astronomers can learn more about the processes that govern stellar evolution and the factors that influence the formation and characteristics of white dwarfs. Future observations and studies of Omega Centauri and its white dwarfs will be crucial for unraveling the mysteries of these enigmatic objects. Advanced telescopes and instruments may offer new data on the composition, distribution, and origins of white dwarfs, shedding light on the complex history of this fascinating star cluster. The mystery of Planet 9. In the vast expanse of our solar system, where planets and moons orbit in a delicate ballet, there exists a tantalizing mystery that has captivated astronomers and enthusiasts alike, the hypothetical Planet 9. This elusive world has sparked intense interest due to its potential impact on our understanding of the solar system's structure and formation. Despite extensive searches and sophisticated tools, Planet 9 has yet to be directly observed, and its existence remains inferred from a series of intriguing orbital anomalies. The quest for Planet 9 began with the observation of unusual orbital patterns among distant objects in the solar system, particularly in the region known as the scattered disk. This distant region, filled with icy bodies and remnants from the early solar system, showed peculiar clustering in their orbits that did not align with the predictions of existing models. These anomalies suggested that a large, as yet undiscovered planet might be influencing their trajectories. In 2016, the hypothesis gained further traction when two astronomers, Konstantin Batygin and Mike Brown, proposed that these orbital discrepancies could be explained by the presence of a massive planet located far beyond the orbit of Neptune. According to their calculations, Planet 9 could be up to 10 times the mass of Earth and orbit the Sun at an average distance roughly 20 times farther than Neptune. This hypothetical planet, if it exists, would exert a gravitational pull strong enough to account for the observed orbital alignments of these distant icy objects. Despite the theoretical groundwork laid by Batygin and Brown, no direct evidence of Planet 9 has yet been found. The challenge of detecting such a distant and faint object is immense. At such great distances, the light reflected by Planet 9 would be minimal, making it difficult to spot with current telescopes. Additionally, its potential location in the far reaches of the solar system means that it might be obscured by the brightness of nearby stars or other celestial objects. To date, astronomers have used various methods to search for Planet 9. Observational campaigns using powerful telescopes have scanned large portions of the sky in hopes of spotting this elusive planet. Surveys of the night sky have also been conducted to detect any potential perturbations or movements that might indicate the presence of a new planet. Despite these efforts, Planet 9 remains a ghostly presence, unseen yet compelling. The search for Planet 9 also involves indirect methods, including computer simulations and models that help refine the predicted location of the planet. By analyzing the orbits of known distant objects and adjusting their models based on different potential locations for Planet 9, astronomers aim to narrow down the search area. These simulations provide valuable insights into where Planet 9 might be hiding, and how it might influence the orbits of other celestial bodies. In addition to its potential location and mass, the nature of Planet 9's orbit is another subject of intense speculation. The hypothetical planet is believed to have a highly elongated orbit, taking it far from the Sun at certain times and bringing it closer during other periods. This wide range in distance could explain the long gaps between sightings and make the planet even more elusive. The implications of discovering Planet 9 are profound. If found, it would provide crucial insights into the formation and evolution of our solar system. The existence of a massive, distant planet could shed light on the processes that shape the early solar system and the distribution of material within it. Furthermore, Planet 9's gravitational influence could offer clues about the formation of other distant objects and their interactions with the solar system's outer reaches. The search for Planet 9 also holds broader significance for our understanding of planetary systems in general. The existence of such a distant planet could inform theories about the formation and dynamics of exoplanetary systems, planets orbiting other stars. By comparing the characteristics of our solar system with those of other systems, scientists can gain a deeper understanding of the common processes and unique features that govern planetary formation and evolution. The dark matter halo of the Milky Way. In the intricate and vast expanse of the Milky Way, our galaxy is not only a swirling mix of stars, planets, and cosmic dust, but is also enveloped in an unseen, mysterious halo of dark matter. This enigmatic substance is thought to constitute about 85% of the universe's mass and exerts a crucial influence on the structure and dynamics of galaxies. Yet recent studies have revealed puzzling discrepancies in the density and distribution of the dark matter halo surrounding the Milky Way, challenging long-held theories and opening new avenues of inquiry. Dark matter was first proposed to explain the observed rotation curves of galaxies. When astronomers measured the speed at which stars and gas orbit the centers of galaxies, they found that the velocity remained high even at large distances from the galactic center. This was contrary to expectations based on the visible matter alone. To account for this, scientists hypothesized the presence of a vast halo of dark matter surrounding galaxies, exerting gravitational forces that could explain the observed motions. The Milky Way's dark matter halo is believed to extend well beyond the visible edge of the galaxy, enveloping it in a roughly spherical cloud. According to traditional models, this halo should have a relatively smooth distribution of dark matter, with density gradually decreasing as one moves further from the galactic center. However, observations and simulations have revealed a more complex picture that does not align with these expectations. One significant discrepancy involves the density of the dark matter halo. Models suggest that the halo should have a certain density profile, with higher densities near the galactic center and decreasing towards the outskirts. Yet, measurements of the velocities and positions of distant stars and globular clusters indicate that the dark matter density might be lower than predicted in certain regions. This discrepancy has led to questions about whether the traditional models of dark matter are accurate, or if there are additional factors at play. Another puzzle concerns the distribution of dark matter within the halo. Simulations and observations suggest that the halo may not be as uniform as once thought, Instead, it could contain substructures such as clumps or streams of dark matter, which could influence the overall distribution and density. These substructures might have formed from the merging of smaller dark matter halos or interactions between different regions of the halo. Such irregularities could affect the gravitational forces experienced by stars and other matter within the Milky Way, potentially altering the dynamics of the galaxy. Theories about dark matter's distribution have also been challenged by recent data from the Gaia spacecraft. Gaia's precise measurements of stellar positions and velocities have provided a detailed map of the Milky Way's structure. These observations have led to new insights into the galaxy's halo, revealing unexpected patterns in the distribution of stars and other matter that could be linked to dark matter. For instance, the discovery of large, coherent structures within the galaxy's halo may suggest that dark matter influences the formation and alignment of these features in ways that were not fully understood. These discrepancies in the expected density and distribution of dark matter around the Milky Way have significant implications for our understanding of both dark matter and galaxy formation. If the traditional models of dark matter are incorrect, it may mean that our current theories about the nature of this elusive substance need to be revised. This could lead to new hypotheses about dark matter's properties, its interactions with visible matter, and its role in the formation and evolution of galaxies. The challenges in understanding the Milky Way's dark matter halo also extend to broader questions about the universe. Dark matter is a key component in our models of cosmic structure formation. It influences the way galaxies form and cluster, affecting the large-scale structure of the universe. Discrepancies in the dark matter halo of the Milky Way could have implications for our understanding of dark matter in other galaxies and the universe as a whole. Researchers are employing various strategies to address these challenges. Improved observational techniques, such as more advanced telescopes and space missions, aim to provide clearer and more detailed data on the distribution of dark matter. Additionally, new theoretical models and simulations are being developed to account for the irregularities observed in the Milky Way's halo. These models incorporate factors such as substructures, interactions with other galaxies, and potential modifications to dark matter's properties. In the end, the mystery of the Milky Way's dark matter halo serves as a reminder of the complexity and wonder of the cosmos. The Cannonball Nebula. The Cannonball Nebula, also known as NGC 3576, presents an unusual and captivating sight within the cosmic landscape. Unlike the familiar, more spherical or diffuse nebulae, the Cannonball Nebula stands out with its distinctly irregular shape that resembles a cannonball. This nebula, situated in the constellation of Scorpius, is characterized by its strikingly asymmetric structure and high-velocity ejections of material, which defy our conventional understanding of nebula formations. When first observed, the Cannonball Nebula's most noticeable feature is its elongated cannonball-like structure. The nebula appears to be compressed along one axis, giving it a shape that is far from the typical round or oval forms usually seen in stellar nurseries. This odd shape is the result of its complex internal dynamics and interactions with its surrounding environment. At the heart of the Cannonball Nebula is a massive star known as an O-type star, which plays a critical role in shaping the nebula's distinctive features. The high-velocity material ejections from the Cannonball Nebula further contribute to its enigmatic nature. Observations reveal that the nebula is expelling material at speeds far greater than those observed in most other nebulae. This high-velocity outflow creates dramatic sweeping arcs and filaments that extend far beyond the nebula's central core. The cause of these powerful ejections remains unclear, posing a significant challenge to astronomers and astrophysicists attempting to unravel the nebula's mysteries. One leading theory suggests that the high-velocity material ejections are driven by the intense stellar winds and radiation from the central O-type star. O-type stars are known for their extreme temperatures and strong stellar winds, which can exert immense pressure on the surrounding gas and dust. This pressure might be sufficient to accelerate material to high velocities, creating the observed outflows. However, this explanation doesn't fully account for the nebula's irregular shape and the specific patterns of material ejection. Another hypothesis involves interactions between the Cannonball Nebula and nearby stars or other nebulae. The nebula's position within a dense star-forming region might subject it to gravitational influences and shock waves from neighboring stellar objects. These interactions could potentially distort the nebula's shape and contribute to the unusual velocity of material ejections. Yet, there is limited observational data to confirm these interactions and their impact on the nebula's structure. The Cannonball Nebula also raises questions about the life cycle of such structures. Most nebulae are thought to evolve through predictable stages, from the initial formation of stars to the dispersal of gas and dust as the stars age and die. The Cannonball Nebula, however, appears to be in a relatively rare phase, where the high-velocity ejections and irregular shape suggest a more dynamic and less understood evolutionary process. This atypical behavior might provide new insights into the diverse ways in which nebulae can evolve and interact with their environments. Furthermore, the Cannonball Nebula's irregular shape and behavior challenge our understanding of the physics involved in nebula dynamics. Theories about nebula formation and evolution are typically based on models that assume more regular, symmetrical structures. The Cannonball Nebula's deviation from these expectations prompts scientists to reconsider and refine these models to better account for such anomalies. Observing the Cannonball Nebula has also been instrumental in advancing our knowledge of high-energy astrophysics. The high-velocity material ejections offer a unique opportunity to study the effects of extreme stellar environments on surrounding matter. By analyzing the speed, direction, and composition of the ejected material, researchers can gain valuable insights into the physical processes occurring within the nebula and the influence of its central star. The intergalactic magnesium. In the vast and seemingly empty spaces between galaxies, known as intergalactic space, astronomers have made an unexpected discovery: high concentrations of magnesium that challenge our current understanding of cosmic processes. These findings reveal an intriguing puzzle, as magnesium is a key element whose abundance and distribution should align with known stellar and galactic phenomena. Yet, the observed concentrations in intergalactic space defy existing models and theories. Magnesium is an element commonly found in stars and galaxies, produced in the cores of massive stars and dispersed into space through supernova explosions. It plays a crucial role in the formation of stars and the chemical evolution of galaxies. Typically, magnesium is expected to be found in higher concentrations within galaxies, where stellar processes actively contribute to its abundance. The traditional view suggests that magnesium and other elements should follow a pattern of distribution closely tied to the life cycle of stars and the dynamics of galactic environments. However, recent observations have detected unexpectedly high levels of magnesium in the vast stretches of intergalactic space. This discovery is surprising because intergalactic space, being so remote from the dense regions of galaxies, was not expected to contain such significant concentrations of elements like magnesium. The presence of these elements raises questions about how they ended up in these otherwise barren regions. One possible explanation involves the idea that magnesium might be traveling through space in a different form or through previously unrecognized processes. For instance, it could be that magnesium is being expelled from galaxies in a manner not previously understood. This could occur through powerful galactic outflows, where material is ejected at high speeds from the centers of galaxies, carrying elements like magnesium into the intergalactic medium. Such outflows might be more prevalent or more efficient than previously thought, distributing elements over much larger distances. It is also a possibility that these high concentrations of magnesium could be the result of ancient cosmic events, such as interactions between galaxies or the remnants of previous galactic collisions. When galaxies collide or interact, they can trigger massive star formation or supernovae, which might release substantial amounts of magnesium into intergalactic space. These events could leave behind traces of magnesium that remain detectable even in the relatively empty expanses between galaxies. There is also the consideration that we might be encountering previously unknown cosmic processes or mechanisms. The way elements like magnesium are distributed throughout the universe could involve complex interactions that are not fully understood. For example, there might be unknown types of cosmic dust or plasma that contain high concentrations of magnesium, influencing how these elements are dispersed across intergalactic space. Understanding the high concentrations of magnesium in intergalactic space has broader implications for our knowledge of cosmic chemistry and galaxy evolution. It challenges existing models that predict how elements are distributed throughout the universe and how they interact with different cosmic environments. These findings might prompt a re-evaluation of how we think about the movement and mixing of elements on a cosmic scale. To address these questions, scientists are employing a range of observational and analytical techniques. Advanced telescopes and instruments are used to measure the light from distant regions of space, allowing researchers to detect and quantify the presence of magnesium and other elements. Additionally, simulations and models are being refined to incorporate new data and explore how different processes could contribute to the observed concentrations. The discovery of high levels of magnesium in intergalactic space also highlights the importance of exploring and understanding the universe beyond the well-trodden paths of galaxies and stars. Intergalactic space, often considered a void, is proving to be a rich field of study with its own unique phenomena and mysteries. As our observational tools and techniques continue to improve, we may uncover more about the intricate processes that shape the distribution of elements across the cosmos.